Welcome to chapter 8. So it's finally we are going to enter the gates of real computer architecture. Where real computer architecture means that we will actually look at designing a processor. So the so this is part of chapter 8 of the book Computer Organization and Architecture, published by McGraw-Hill in 2015. The important feature of this chapter is that we will look at designing a full working processor for the simple RISC instruction set from scratch. So you will find models of this processor in both Logisim as well as in VHDL in the website of the book, which is given over here. And but the main aim is starting from first principles ab initio. We want to design a full working processor that can run fairly complicated programs. Let's now consider the outline of this particular chapter. So we shall start with the overview of a processor, where we shall describe all the features that are required to implement a simple RISC processor. Then we shall look at the detailed design of each stage, focus on the control unit after that. And subsequently, we shall describe a different type of processor that is, it's the same processor designed for the same ISA, but the style of designing it is very different. So it's called a microprogrammed processor. So a lot of the current processors do have microprogrammed features. It's a very important thing to learn. So a microprogrammed processor will have its own microassembly language and its own microcontrol unit. So we shall take a look at this towards the end of this particular chapter. So let's take a look at processor design. So the aim of designing a processor with transistors and all the logic gates that we have learned, and also using all the digital elements that we have learned in chapter 6. So the main aim is to implement the entire simple RISC ISA. So we will get the instructions in the binary format, in a 32-bit binary format, and we need to provide as much of performance as possible, where performance is defined as inverse of the execution time of a program. So we want programs to pretty much run as fast as possible. So the basic approach is to divide the processing of an instruction into several stages and look at each stage and design each stage separately. So let's look at a car assembly line. So in a car assembly line, we typically have different shops, right? So we have one shop that casts raw metal into the chassis of a car, the chassis of a car. Then another shop builds the engines. Another shop builds the body. Another shop, does the dashboard and upholstery. And finally, one group of people put everything together. And at the end of a car's assembly line, it goes through, it's finally painted, right? Painted and tested, and then it's ready for delivery. So similarly, an instruction also goes through various stages. At each stage, some amount of processing is done to an instruction. And then from that stage, it moves to the next stage, subsequent stage it moves. So similarly, we can divide a processor into multiple stages. So it is typical to divide the processing of an instruction into 5 stages. So here we start with the instruction fetch stage. In the instruction fetch stage, we fetch the instruction from memory. So we will call this the IF stage, the instruction fetch stage, or the IF stage. The next stage will be the operand fetch stage, that we shall call the OF stage, where we fetch the operands, be it registers, registers, not memory addresses, but registers, and also blow up constants and immediates and all of that. So we'll fetch the operands in this stage. In the EX stage, EX standing for execute, we shall execute the instruction, right, run it. The fourth stage will be a memory access stage, where we will access memory, perform a load or store. And finally, the fifth stage will be called a register write stage, where the results of the instruction will be written back to the register file. So these are the five stages: IF for instruction fetch, OF for operand fetch, EX for execute, MA for memory access, and RW for register write. It's also known as the write back stage, the last stage. So the instruction fetch stage, IF stage, what does it do? It fetches an instruction from instruction memory and it computes the address of the next instruction. The operand fetch OF stage does several things. First is it decodes the instruction. Decoding the instruction means you break it into fields, because everything is packed inside a 32-bit field. So we need to break it into fields. Then we need to fetch the register operands from the register file, so we need to read them. So this stage also computes the branch target, which adds the offset to the program counter. So if any of these terms sort of look foreign, then the reader is requested to go back to chapter 3 and take a look at the simple RISC ISA once again, because we are pretty much designing a processor for the simple RISC instruction set. So it is important for the reader, if the reader has forgotten, to go back to chapter 3 and sort of recapitulate these terms. So what we shall do here in the OF stage is several things. First is decode, fetch the operands to the register file, compute the branch target, which is essentially the ID of the instruction after the branch. So in this case, we add the offset to the program counter. We also in this stage compute the immediates. So the immediate, mind you, in simple RISC is 16 bits plus 2 modifiers. So it's an 18-bit immediate in that sense. So everything inside the processor is 32 bits. So pretty much these 18 bits need to be, in a sense, expanded and blown up to a 32-bit quantity. So this is called expansion of the immediate. So we need to compute the immediate, which is 16 bits plus a 2-bit modifier. So I shouldn't call it a 2 modifiers, I should call it a 2-bit modifiers. That's slightly that's slightly better. So we also have 2 modifiers, so that is also not wrong. So our 2 modifiers are, we have a U modifier where we treat the 16-bit quantity as unsigned, and we have the H modifier where we essentially the 32-bit constant that we create, in that the 16 bits are loaded in the upper 2 bytes. Alright, so this immediate that we have, that needs to be expanded after taking the modifiers into account into a 32-bit quantity. So the default behavior is to extend the sign, but we can overwrite this default behavior with the U and the H modifiers in the instruction. And finally, we also need to generate control signals, but we shall see that later. The main aim of the OF stage is thus to understand the instruction, fetch the operands, compute the 32-bit branch target and immediate after taking the immediate modifiers into account. Now let's take a look at the EX stage. So the EX, or the execute stage, contains an arithmetic logical unit, an ALU. So the unit can perform all arithmetic operations: add, subtract, multiply, divide, compare, OR, and so basically all, this should actually be instead of an OR, it should actually be a mod. So it can find essentially do a division and find the remainder, and all the logical operations which are AND, OR, and NOT. So the execute stage also contains the branch unit for computing the branch condition. And so basically, if you would recall, we have 2 conditional branch instructions in simple RISC called BEQ and BGT. So BEQ basically means branch if equal, and BGT means branch if greater than. So, so basically, if one of the last comparisons, so not one of the last, if the last comparison has resulted in an equality, then the BEQ condition will be true. Otherwise, the if the last comparison has resulted in a greater than, then the BGT condition will be true. So this is also done in the EX stage, and the EX stage also contains the flags register, which is updated by the compare instructions. So just to summarize, the execute stage contains the arithmetic logical unit primarily. So the ALU does arithmetic operations: add, subtract, multiply, divide, compare. It finds the remainder, the mod, and it does logical operations, which is AND, OR, and NOT. Along with that, it processes the branch conditions for the BEQ and BGT instructions, branch if equal and branch if greater than instructions. So in this case, it essentially reads the flags register to find out the result of the last comparison, and on the basis of that, a decision is taken. Subsequently, we have the MA, the memory access stage, which interfaces with the memory system and executes a load or a store. And we also have the RW stage at the end, the fifth stage, which writes to the register file. And in the case of a call instruction, when we are calling, so recall that in the case of a call instruction, the address of the next instruction was saved in the return address register RA. So it will basically write, it writes to register RA. What does it write? The address of the next instruction. The address of the return address is written into register RA. So now let's consider the detailed design of each stage. So let's take a look at the circuit diagram of the IF stage or the fetch stage. So we'll also call it the fetch unit. So in this case, we will be showing the circuit diagram. So we'll be seeing similar circuit diagrams in for almost all the stages. So it's important to have an understanding of the way that these diagrams are drawn. So essentially, each box determines is either a storage unit or a compute unit, and we will be using this sign for a multiplexer. So recall, a multiplexer is a logical unit that chooses one of the two inputs. So at the negative edge of a clock, so we assume that all our circuits are negative edge triggered. So whenever the clock goes from positive to negative, a computation starts. So the PC, we'll call the PC as the program counter registers. It's a 32-bit register. So the PC flows to the instruction memory. The instruction memory is typically an array of SRAM cells. So we'll be discussing on how this instruction memory is created in chapter 10. But for the time being, let's assume that it's a black box that we don't have to touch, and which is per se out of the fetch unit. So we read an instruction from it, which is again a 32-bit quantity. So we'll be using this symbol over here to indicate that the wire is carrying 32 bits. So we'll read the instruction, and simultaneously we will consider the program counter's address and add 4 to it. So why will we add 4 to it? Because we want to get the address of the next instruction, of course assuming it's not a branch. And so since each instruction is 4 bytes and we address memory at the level of bytes, we'll add 4 to it. So this will be one of the inputs to the multiplexer. The other input to the multiplexer will be the program counter, the PC of the branch, called branch PC, which is also a 32-bit quantity. So if the instruction is a branch, the branch target needs to be chosen, right, which we are calling the branch PC. Or if it's not a branch, we need to choose the next instruction, which is the current PC address plus 4. So the multiplexer will choose one of the addresses depending upon whether the instruction is a taken branch or not. And so there will be, so we'll be using this dotted lines here to indicate the control signals for controlling the multiplexers. So we're assuming a signal called isBranchTaken, which is coming from another stage. So this will say if it's a taken branch, then essentially this value flows out. If it's a not taken branch or not a branch, then PC plus 4 is what flows out. So this controls the multiplexer. Only one of the inputs will show up at the output, and this again will be the value of the next program counter that will be used in the next cycle for the next instruction. So this is the fetch unit. The fetch unit per se is fairly simple. The important points to note is that we'll be using these dotted arrows for the control signals for controlling the multiplexers, and we'll be using the multiplexer will have a 0 input and a 1 input, basically to say that if isBranchTaken is 1, we use the branch PC. Otherwise we use PC plus 4 as the input, which will show up at the output. So pretty much that's all. It's a fairly simple circuit with one register, one adder, and one multiplexer. So that's almost, as simple as it gets. So the fetch unit, I just want to repeat, contains a register called the PC register, which is negative edge triggered, and the multiplexer chooses between PC plus 4, the contents of PC plus 4, and the branch target, which is called the branch PC, and it uses a control signal called isBranchTaken. Let's now consider the isBranchTaken signal. So the isBranchTaken is a control signal which is generated by the EX unit. So its job is to control the multiplexer in the IF stage. So basically this is how isBranchTaken is set. So if it's a non-branch instruction, so the value of isBranchTaken is 0, so it's not a taken branch. For these three kind of instructions, call, ret, and B, an unconditional branch, these are always taken. So isBranchTaken is 1. For the B, Q, and BGT instructions, which are conditional branch instructions, if the branch is taken, then isBranchTaken is equal to 1, as we can see over here. And if the branch is not taken, then the value of the isBranchTaken signal is 0. Alright, so isBranchTaken basically says whether it's a taken branch or not. If it is not taken because B, Q, and BGT evaluate to false, or it's not a branch instruction, the value of isBranchTaken is 0, otherwise it is 1. So let us now define two very important concepts that we shall keep seeing over and over again in different forms. They are the data path and the control path. So the data path essentially consists of all the elements in a processor that are dedicated to storing, retrieving, and processing data, such as the register files for keeping the registers, the memory, the ALU, and also in this case the program counter registers, and so on. So the control path is essentially what consists of the dotted lines. So the control path primarily contains the control unit, whose role is to generate the appropriate signals to control the movement of instructions and data in the data path. So let's come back to this diagram. So in this diagram, all of this is there in the data path, right? All of this. What is there in the control? So this is like the data path, right? All of this, which essentially consists of the signal to control this multiplexer, and also the control unit that generates this signal, they comprise the control path, right? So the control unit and these wires to control the multiplexers, they are part of the control path. So whether the multiplexer per se should be a part of the data path or the control path, well, that depends on the interpretation, but we would like to keep it in the data path because that is like the data path is like the static aspect of the circuit. So consider the data path as the network of roads, and consider the control path as the traffic lights and the controllers of the traffic lights. So network of roads pretty much is a static entity, but the traffic lights control how the cars flow in the network. So we can think of the control path as something similar inside a processor. Alright, so now that we have the data path and the control path, so the control path has a control unit, and it has an interconnection network where it sends wires to all the elements inside the data path. So this controls the movement of data and movement of instructions and values and everything inside the data path, similar to what we have in a traffic network, right? So traffic network is a data path, the cars are the instructions themselves, and the controllers for the traffic lights and so on are part of the control path. So currently we are looking at what's called a hardwired control path, in the sense that the control path is fixed, it cannot be changed, it is made in silicon and it cannot be changed, so that staticness to the control path is there, that it cannot be modified. But when we look at a microprogrammed processor, we'll see that aspects of the control path will be exported to the programmer. So in a sense, the control path can be modified and controlled. So we'll take a look at that later, but let's take a look at this approach, which is by far more common, which is to have a hardwired control path, which means that once the chip has been designed and fabricated, the control path cannot be changed. So it cannot be reprogrammed. So let's take a look at the operand fetch unit now. So we have finished the instruction fetch unit. This is the second stage, the operand fetch unit. So let's just take a quick look at simple risks instructions. So these are all our arithmetic instructions that we have: add, subtract, multiply, divide, and get the modulo, the remainder. All of them have the same format. We first have the destination register, then we have the first source register, subsequently we have the second source, which can either be a register or an immediate value. The immediate value is actually an 18-bit quantity. The 18 bits are divided into two fields, 16 and 2. So it's a 16-bit constant, and we have space for 2 modifiers plus the default one, so 3 modifiers. So that takes 2 bits. Then we have the compare instruction. So there actually should be a space here, right? So it's compare space rs1 comma. So this is rs1 is register source 1, and rs2 slash immediate is either a registered source or an immediate, a constant value. Then we have some logical instructions, and, or, and, not, which have exactly the same format as the arithmetic instructions. We have the move instruction to move data from a register or an immediate into another register. These three, LSL, LSR, and ASR, are the three shift instructions. They have exactly the same format as the rest of the arithmetic instructions. We have a no-op instruction which does absolutely nothing. The benefit of a no-op instruction will be clear in chapter 9, which is the next chapter on pipelining. Till that point, we'll not be able to understand what's the greatness of a no-op instruction. The load and store instructions over here, load is used to read something from memory, and the store instruction is used to write something back to memory. So they have the same format. So mind you, we had made an exception for store, in the sense that store actually does not have a registered destination. Its destination is memory. But we didn't want to change the format, so we use the same format. We use RD as the register to which we want to load, and we use RD as a source register in the case of store. So we shall see that this will slightly complicate our processor design, not a lot, but slightly. We'll use the immediate as the constant offset and use RS1 as the base register. We have 5 branch instructions. So B, Q, BGT, and B are the two conditional and one unconditional branch instruction. So B, Q, and BGT require, we need to know the results of the last comparison, and B is an unconditional branch. Call is for a function call, and ret is for returning from a function. So let me now add a word of why. So for every instruction we assign it a code. So how many instructions we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is empty. We have 21 instructions. So we have 21 codes for the different instructions. And so since we have 21 instructions, we require 5 bits. So that's the reason we have 5-bit code, and this code is also called the opcode. Right? It's a traditional name for the code of an instruction, opcode or operation code. So this 5-bit opcode that we have uniquely identifies an instruction. So the question is, why have we given the opcodes to the instructions the way that we have? So let's take a look. Let's take a look at the branch instructions first. So essentially we need to look at decode complexity. So if we take a look at the branch instructions, we'll see that all the branch instructions that we have been given an MSB of 1. So in that sense, it's very easy to find if an instruction is a branch or not. We just need to take a look at the most significant bit of the opcode and see if it's 0 or 1. So that's very easy. To find out if an instruction is a load or a store, you will see that they have been given consecutive opcodes. So we actually need to verify and look at the first 4 bits. If the first 4 bits are 0, 1, 1, 1, then we will know it's a load or a store. So that will also tell us that we need to access the memory access stage. And similarly, we have a quick way of finding if an instruction is a shift or something. And so that's essentially, in opcode design, we have to look at how easy it is to understand and how quickly we can decode an instruction and understand it. So it is always a good idea to group similar instructions, give them similar opcodes. For example, all the branch instructions, we have given them an MSB most significant bit of 1, which has made our instruction design, in a sense, actually very easy. It's very easy to find out if an instruction is a branch or not. We just take a look at its MSB, most significant bit. And for load and store also, we have to take a look at its first 4 bits, but that's also easy. That's not very hard to do. So the instruction formats that we have is, we have 3 instruction formats. We have a branch format. So the branch format, so always the 5-bit opcode is the top 5 bits, bits 28, 29, 30, 31, 32. That's always the case. We then have, in the case of a branch, we have a 27-bit offset. So it's actually a word offset, not a byte offset. For a word is units of 4 bytes. Then we have the register format. So in the register format, we specify whether it's an immediate or not. So the immediate bit is actually set to 0. So I can sort of write 0 over here, and I can write 1 over here for the immediate bit. Then we have the register destination, register source 1, register source 2. In the case of an immediate format, which is exactly the same, at least the first part, we have the register destination, the first source register, and then we have the 18-bit immediate, which is again divided into 2 fields. So each format needs to be handled by the decode circuit in the OF stage separately. So now let us take a look at, so then the next part, after doing a little bit of decoding is in the OF stage, is to read the contents from the register file. So let's take a look at what's happening. So given an instruction, if we consider bits 19 to 22, so 19 to 22 is RS1 and 15 to 18 is RS2. So what we do is we assume a register file. A register file is basically a set of registers. So that's called a register file. So we have 16 registers in simple RISC. So the register file will contain 16 registers. And so here it will have two read ports. A read port basically means that two register IDs can be given to the read port, and we can sort of read the values of two registers simultaneously in a single cycle. So A is for the address of the register, which can be any number between 0 and 15, and D is for the data that was there in the register. So the address is typically a 4-bit quantity between 0 and 15, and the data is a 32-bit quantity, which is the contents of the register. So we'll call the two contents OP1 and OP2. So the idea is that given an instruction, we'll have two. So let's consider the first input. So in the first input, we'll have either RS1, which is the first source register, or we need to take a look at, so let's take a look at the ret instruction, the return instruction. So what the return instruction does is that it reads the value of the register RA, or register R15, right? RA or R15, same thing. So basically the contents of register RA are transferred to the PC. That's exactly what the return instruction does, that whatever address is stored inside the return address register, that becomes the contents of the program counter in the next cycle. In effect, the function returns and go back to the instruction just after the call instruction. So it is necessary to read the contents of RA. So that's the reason we have a multiplexer. Inside the multiplexer, if this isRet signal is true, isRet means is returned. So if this signal is true, this means that this is a return instruction, a ret instruction. So we choose RA, which is 15, as the output of the multiplexer. If the instruction is not a return instruction, we choose RS1, which as the output of the multiplexer. All right. So once again, what does this multiplexer do? It chooses between RS1, which is the first source register, and it chooses between 15, which is the default source for the ret instruction. And mind you, there will be the ret instruction does not need RS1, so we can get away with this. So this goes to the address port of the read port 1 of the register file, and then we read the data out, and this value we will refer to as OP1. Now let's take a look at the second multiplexer. So mind you, we had done a special case. So second multiplexer will be a default input, which is RS2, the second source register. Going back, we see that the second source register is between bits 15 to 18. So that is the ID of the second source register. But also in the case of the store instruction, we had actually done something very interesting. In the immediate format, we had assumed that for the case of the store register, we'll actually have the store instruction. We'll actually write it in this form: store rd immediate rs1. So store did not have an rs2 register source 2 field, and the rd is pretty much a source. It's not a destination. So we're reading the contents of register rd and saving it in memory, right? So the store instruction has actually two register sources, which are rd and rs1, right? So these are the two register sources of the store instruction. So the complexity that this introduces is that we need to add a multiplexer. If the instruction is store, we will then consider this output with 1. We will read in rd. So mind you, rd is this instruction over here. So basically, let me give one more example if it's still not clear. So let's assume we have an instruction of the form store r1. So in this case, R1 is a source register which needs to be read, and then we need to compute the memory address by taking the contents of R2 and adding 20, and we need to effect a store. So the field in which R1, which is 0001, will be stored, this field is RD in the instruction, and R2 will be stored in the field, which is this field RS1. So basically the sources in the store instruction are RD, which is bits 23 to 26, and RS1, which is bits 19 to 22. So that's the reason the store instruction will use the RD field, which is bits 23 to 26, as the input for the register files read port 2. If it's not a store instruction, then the input will be the second source register, which is RS2. So mind you, it is always possible that we are only using, we have only one register source. So in this case, we are doing some amount of extra work in producing a junk value, but that is still fine because it's not going to corrupt the output of the instruction itself. So doing a little bit of extra work in the name of simplicity is still fine. So once we have done this, so the second input, as you can see, can either be RS2 or RD. Basically, to take store instructions into account, we read the value, and the value will be a 32-bit quantity, which we shall henceforth refer to as OP2. So to summarize, in this slide, we are showing the register, the circuit for reading the register file. So we needed to add two multiplexers to the left of the register file to basically take some special cases into account. For the first read port 1, we took into account the fact that the isRet instruction reads the return address register. So we need to choose between the return address register and the first register source RS1. So that's the reason we have a multiplexer with the isRet signal. Similarly, for read port 2, we have a multiplexer with the isStore signal, which chooses between RD or RS2. If it's a store, RD is the source which needs to be read, and if it's any other ALU instruction, then RS2 is a source that needs to be read. So then we read it from read ports 1 and 2 simultaneously, and the data comes out, which are referred to as OP1 and OP2 respectively. Let me now repeat what was said in the previous slide. So the register file has two read ports. So they take the two inputs. The first read port, whose output is OP1, is the branch target in the case of a ret instruction. So in the case of return instruction, it's actually the return address, the branch target, or the return address in this case, or it is the first source register RS1. OP2 is the value that needs to be stored in the case of a store, or it is the second register source RS2. So now let's take a look at the immediate and branch unit, whose job is to compute the branch target or the immediate. So this is in the OF stage. So what we have coming in from the IF stage is the instruction. So from the instruction, what we do is that for the case of a branch, we remove the opcode. So 27 bits are left. Since this is a word offset, not a byte offset, we shift the number by 2 bits and extend the sign. So by shifting it by 2 bits, the reason we do it is because it's an offset in terms of memory words, and one memory word is 4 bytes. So what we do is we take a 27-bit quantity and we shift it to the left by 2 positions, so we get a 29-bit quantity, and then we extend its sign to make it a 32-bit number. So this is essentially the offset in terms of bytes. We add this to the program counter to give us the branch target. So the branch target is the program counter plus the offset, and mind you, the offset was in terms of memory words, so this was made an offset in terms of bytes, and it was extended to 32 bits. So in this case, we compute the branch target. So mind you, we do this even for non-branch instructions, because at this point, we do not know for sure if the instruction is a branch or not a branch. So it always helps if we do some amount of extra work, which might get wasted if the instruction is not a branch. But nevertheless, in the interest of time, it needs to be done. So it's a little bit of wasted work, but it's still fine. The case of an immediate is slightly more complicated. So we again extract the bottom 18 bits. This is done for all instructions, irrespective of whether it has an immediate or not, because at this point we do not really know if an instruction has an immediate or not. So what we do is we calculate the immediate. So the way that we do is that we consider the 16-bit constant and the 2-bit modifiers. So based on that, we create a 32-bit number. So just to repeat, if it's a default modifier, then what we do is that we take the 16-bit specified and we essentially extend its sign with the sign bit. We sign extend it. So this is a default modifier. If it's the unsigned modifier, what we do is that we write the 16 bits in the lower 2 bytes, and in the upper 2 bytes we just write zeros. If it's the H modifier, what we do is that we write the 16 bits in the upper 2 positions, and in the lower 2 bytes we write zeros. So in this way we create a 32-bit constant by extending the immediate, and we call it imx. So these fields are computed for all instructions, might contain junk in the case of some instructions. And after doing that, we are done with the OF unit. So the way it stands is that we have the fetch unit, the instruction fetch unit on one side, and we have the execute unit on the other side. So, and we have two main components or subsystems in the operand fetch unit. So the first is the register file. So register file contains the registers. So in that we read the values of the registers. It takes two control signals as input, isRet and isStore. And there are two outputs, OP1 and OP2. So depending upon the instruction, they can contain different things. So in the case of a normal ALU instruction, they contain the first and second registered source operand. And if it's a return instruction, OP1 will contain the return address. And if it's a store instruction, OP2 will contain the register whose value needs to be stored, and OP1 will contain the base register. So in any case, let's refer to these fields as OP1 and OP2. Then we have a branch and immediate unit where we compute the branch target by adding the offset to the PC, and we compute the extended immediate, the 32-bit immediate, by expanding the 18 bits that were embedded in the instruction. Additionally, what we do is that we need to compute all of these control signals, isStore and isRet and so on. So we send the opcode and the immediate bit, 6 bits, to the control unit whose job is to generate the signals. So the assumption is that the control unit very quickly generates isRet and isStore such that they can be used in the same stage, and for other stages it can take a little bit more time. Now let's take a look at the execute stage, the EX stage, which also contains multiple units. So let's first take a look at the branch unit, which is very simple. So let's start from the bottom. So let's look at the flags register, which contains mainly 2 bits, the E bit and the GT bit. So the E bit is set if the last comparison led to an equality, and the GT bit, the greater than bit, is set if the last comparison led to a greater than condition, that the first operand is greater than the second. So now let's see. So if the instruction is a BEQ, branch if equal instruction, then the isBEQ signal is set to 1, is set to true. So if this signal is set to true and flags.e, the last comparison, had led to an equality, then this means that it should be a taken branch. So we have an AND gate And this specific wire, the value on this specific wire indicates if it's a taken branch because BEQ is true. So we can say that BEQ, branch if equal, this condition is true because it's a branch if equal instruction. That's number one. And number two, the last comparison led to an equality. Similarly, we can do the same for the BGT instruction. We can see if the last instruction, if the current instruction is a BGT or not. This signal is set by the control unit, and the value comes from the flags register. So we do an AND. So the AND output of the AND gate tells us whether the instruction is BGT, and if the last comparison resulted in a greater than, see both of them are true, then only the output is true. And we consider one more control signal is U branch. U branch means unconditional branch. So what will be an unconditional branch? A branch instruction, just a B instruction is an unconditional branch. If we have a call or return or something, then also it's an unconditional branch, right? So so in that case, but we'll look at call and return later. So let's only consider the B instruction for the time being, is U branch. And so when we discuss call and return, we'll again come back to this slide. So basically, if that is true, which means we are branching in any case, so we do an OR of this. So an OR gate is needed to basically find out whether this is a taken branch or not. If it's a taken branch, right, if we are branching to some other location, then this control signal is set to true. So mind you, this control signal is branch taken, which is going to the IF stage. So let me go back to the IF stage and show you where exactly it was being used. So in the IF stage, if you see, this is branch taken signal, which is essentially coming from the EX stage, is being used to set the value of this multiplexer. So either we choose PC plus 4 or we choose the branch PC. So let's go back. So in this case, what we see is that the isBranchTaken will be set if BEQ or BGT conditions are true, or if it's an unsigned branch. And an unsigned branch can, so what are the instructions which are, sorry, not an unsigned, unconditional branch. What are the instructions for which an unconditional branch condition is true? Is either B or a call or a ret, right? So that's when we know that we are changing the value of the PC for sure. So basically that's when this condition will be true, and these conditions are generated by the control unit. Now let's take a look at this multiplexer over here. So let's assume an isRet signal, which is again generated by the control unit, which says if an instruction is a return or not. So if an instruction is of a type return, then essentially we use OP1 as the branch PC. So branch PC can be thought of as the branch target, right? It's the same thing, the target of the branch where you are branching to. So in this case, if you see OP1, if it's a return instruction, then essentially OP1 is the contents of the return address register, which is essentially the return address. So if it's a return instruction, we use the return address as the target. Otherwise, we use the branch target, which essentially comes from the previous stage, the OS stage. We use the branch target, which is the PC plus the offset, as the branch PC or as the branch target. So basically we are differentiating between the terms branch target and branch PC. The reason we are doing that is because branch target is something that we are computing by adding the offset to the PC. This is the case for almost all the instructions other than, not for almost, for all the instructions other than ret. So BEQ, BGT, B and call the target is embedded inside the instruction. So we can add the PC and the offset to get the branch target. However, the return instruction is special. So in this case, the address where we want to branch to is actually there inside a register called the return address register, which has to be read from the register file. So we read it and we are calling that value OP1. So we need to choose between them with a multiplexer based on the isRead signal, and the field branch PC is generated, which is a 32-bit address, and the branch PC again goes to the IF stage. So if you see the IF stage, you can see that there are two inputs which are coming from the EX stage. One is the branch PC and one is isBranchTaken. So essentially we are making a choice between PC plus 4, which is the default next PC, and the field called branch PC, which is essentially a target of the branch for a taken branch. We are choosing between them depending upon this particular signal, and this is telling us to either choose the default next program counter or choose branch PC. And branch PC is being generated in the EX stage using this multiplexer as is shown based on the values of the isRead signal and data computed from the previous stage, the OF stage. So now let's take a look at the other component of the execute stage, the EX stage, called the ALU, the arithmetic logical unit. So basically it has two inputs, let's call them A and B. The first input is OP1, which is the first source. The second input can either be a register, which is essentially OP2, the second output of the register file, or the immediate, IMEX, which is a 32-bit extended immediate. So we need to choose between them, either for the second source, either a register or an immediate. This is done with the help of the isImmediate signal, which is again generated by the control unit. To choose between a register input and an immediate input, one of them are chosen, and so that is used as an input to the ALU, arithmetic logic unit. So the arithmetic logic unit can do any kind of an arithmetic or logical function, such as add, subtract, multiply, divide, and even and, or, and not, all kinds of arithmetic and logical functions. So there are a set of ALU signals that direct the ALU on what needs to be done. Again, these are generated by the control unit, and the ALU produces a result called the ALU result. So let's take a look at inside the ALU what is happening. So inside the ALU we have many functional units. So what is it exactly that we have? So the most important unit inside the ALU is the adder. So the adder actually does several things. So the adder of course does regular addition. So the inputs to each of these units are actually the inputs to the ALU, which are A and B. So the A and B was mentioned on the previous slide. So here so we'll refer to these two inputs as A and B. So essentially we love giving names to wires. So we have given a name to the first wire as A and a name to the second wire as B. So the adder also takes two inputs A and B. So then we have a host of control signals generated by the control unit. So if we have this signal isAdd as true, means that an addition needs to be performed. We do the addition and the output comes via this wire, right? So this again contains 32 bits. It's not a single wire. So mind you, in the 2's complement world, addition is the same as subtraction, or subtraction is the same, subtraction is the same as addition. So to essentially subtract B from A, to compute A minus B, we essentially need to add A plus the 2's complement of B, which is basically the 1's complement of B plus 1. So any subtraction problem is converted to an addition problem. We'll use the same adder for it, albeit with a little bit of extra circuitry. So the adder can manage that. So we'll have a is sub control signal to subtract two numbers. Then we'll have so this subtraction and comparison is the same thing, in the sense that when we are comparing A and B, what we do is that we subtract B from A, and based on the sign of the result we set the flags. So is compare is the same as is subtract, it's just that it will set the flags. So the flags will have two bits. So if A is equal to B, we'll essentially set bit E to 1, and if A is greater than B, then we will set the bit GT to 1. Otherwise both the bits, the default state of both the bits is 0. So that's the way that we can compare, and comparison and subtraction is the same thing. The only addition with comparison is that the flags in the flags register get set. Also loads and stores use the adder, and that is basically to add the offset to the base register. For example, we have a function of this type, load R1 for R2. So in this case the memory address is essentially the contents of R2 plus 4. So that is exactly what is done over here in the adder to compute the address of loads and stores. In a similar manner the multiplier works, but it does not do many other things. So it just has a single control signal called isMul. Then we have a divider. So the divider can in principle do two things. It can either divide A divided by B, or it can find the modulo or the remainder of A divided by B, what is its remainder. So the quotient can be found out or the remainder can be found out. So it depends on the control signals, which again depends on the type of the instruction. So this is also one of the possible outputs. Then we have a shift unit which can shift the value. So here A and B, A again denotes the particular register that needs that contains the value, and B contains the shift amount. So we can shift it either a logical left shift or a logical right shift or an arithmetic right shift. So they have their corresponding control signals. Then we have a logical unit which computes the results of the OR, NOT and AND functions. So NOT of course will not have a second operand, but the other two, OR and AND, will have two operands. So the logical unit does that. And then we have a move unit which is actually very simple. So what we do is that essentially we do nothing. So we have a single input that comes in. So mind you, this is input B, and the reason that this is input B is because we might move either a register or an immediate into another register. So that's the reason it's input B. So all that the move unit does is it just, so basically the unit acts as a pass through, where the value B simply passes through the unit and goes to the output. So at the end we have a multiplexer which pretty much gets a lot of inputs. So in this case it's getting 6 inputs. Again based on the control signals. So basically this has not been shown because there have been too many arrows. But based on the control signals from the control unit, we need to choose one of them, and that becomes the ALU result. So there is one nice trick via which you actually don't need a multiplexer. So it's called a transmission gate. So the idea here is that, let's say, so what we want to do over here is that we basically want to so one of these lines contains valid data, the rest contain junk data. So we want to choose the line, let's say maybe this line that contains valid data, to become the output. So in a simple transmission gate, the way that it works, actually let me remove the ink on this slide. And so a transmission gate is a good idea, but it's not the only idea of how to implement such a multiplexer. So let's assume there are two inputs of this type, and so let's call this input 1, and let's again call this as input 2. So let's have two transistors back to back. And let this be the output line. And so let the signal that's controlling this be A, and let this be the complement of A, which means both are enabled. Similarly, let this be B and the complement of B. So this structure over here is called a transmission gate. So now, if you would recall our discussion from chapter 6, so let's say that A is 1. See, if A is 1, this transistor, the NMOS transistor is on, as well as A bar is 0. So the PMOS transistor is on. So essentially this input is connected to the output. So the output will take up whatever voltage is there in this input. So all that we need to ensure is that A and B are not on simultaneously, and that can be ensured by not by the control unit. Pretty much don't make A and B on simultaneously. So assume that this A transmission gate is on, in the sense the switch is closed, then input 1 is the same as output. And if B is off, then pretty much input 2 is kept floating. So it'll be absolutely disconnected from the output. So you can think of it that if this is a switch, the switch is absolutely not connected. And similarly, we can connect 10 other inputs to the output wire, and as long as we ensure that one of the transmission gates, which is essentially just a pair of NMOS and a single pair of NMOS PMOS transistors, if one of them is enabled meaning transmitting current, conducting, then pretty much the output will be equal to that input, and the rest of the inputs will be floating. Floating means disconnected with the output. So that's an easy way of making a high input multiplexer. It does have its own problems, but a classic text on electrical engineering is a better source to take a look at transmission gates. But pretty much using transmission gates, we can implement a multiplexer of this sort. And what we want at a high level is that we want the output of the ALU, called ALU result, to be computed correctly. So this pretty much talks about the same thing. Also, this slide talks about power consumption. So the idea is that we do not want all the units of the ALU to be active at the same time, because that would consume a lot of power. Because the instruction will also use only one unit, a single unit. So when is power dissipated? So power is dissipated pretty much when the inputs or outputs make a transition from 0 to 1 and 1 to 0. So why is this the case? Because only when there is a transition, there is a flow of current. And whenever there is a flow of current, there are resistive losses in the circuit, and essentially heat gets dissipated. So what we need to do is that we can avoid a transition by not letting the new inputs propagate to units that do not require them. So in a certain sense, if a unit, consider maybe a multiplier that is not being used, so if let's say its inputs are not changed, in the sense they are just kept floating, disconnected from the inputs to the ALU, so they will maintain their previous voltages and the output will remain the same. So since there is no transition, we will not lose any power, and because there is no switching basically means a change in logic levels. So since there is no switching, there will be no wastage or consumption in power. So here again we can use a transmission gate, which is exactly the same thing as we had described earlier. So a transmission gate pretty much contains a pair of gates, an NMOS and a PMOS. So the output is equal to the input if S is equal to 1. Otherwise the output, if this is the output and this is the input, the output is totally disconnected from the input, so you can think of it as an open switch. So in this case also transmission gates can be used to isolate the inputs of the multiplier from the inputs of the ALU. So given that, we can use transmission gates for two purposes. One is to isolate the inputs of a specific subunit inside the ALU from the overall inputs of the ALU to save power. And second, we can build a large multiplexer with the help of transmission gates. It's doable. So let us summarize our discussion up till now. So when the execute unit, the EX stage, contains the arithmetic and logical unit, the ALU. So the ALU takes in the first operand is the first registered source. And the second operand can either be a register or an immediate controlled by the isImmediate signal. Based on the ALU signals, an appropriate operation is done. So the ALU also sets the flags. And so the branch unit reads the flags, and depending upon the type of instruction, whether it's a conditional branch or whether it's an unconditional branch, it computes if it is necessary to actually change the program counter other than the default. So that is the isBranchTaken signal, which says if the current instruction is a taken branch or not. Simultaneously, we also compute the branch PC, which is the final branch target. So that can either be the return address register, which has been read from the register file, or it can be the PC plus the offset embedded in the instruction called the branch target. So in any case, we use a multiplexer to choose between them, and the branch PC goes to the fetch unit for the next cycle. So let us now consider the fourth stage, which is the MA unit or the memory access unit. So the memory access unit is very simple. It has a memory unit which is connected to the data memory. Inside the memory unit, so let's first take a look at the results. What is it that it requires? So what we require is that we need the source. So for loads and stores, we actually require different things. So let's maybe first take a look at loads. So let me erase the ink on this slide. So in the case of a load, what we need is the address. So the address is computed by the ALU. And so the address is the contents of the base register plus the offset which is specified in the immediate. So this is computed inside the ALU, and this comes in and is stored inside a small register, sub-register called MAR, memory address register. So this is the address in the case of a load. So we are discussing the case of a load now. So then the address flows to the data memory. The data memory fetches the value, and it again flows out, and it flows out to the next stage, and this is called the load result. So the load result, so the only input that the memory unit requires in the case of a load is actually the address, is actually the memory address of the load. And after that, so this is in the ALU result field, in the ALU result wire. This flows to data memory and the output comes out. Now, let us consider the case of a store. So in the case of a store, what we shall do is, well, the first thing that we shall do is we shall erase all the ink on the slide and write a big store over here. So a store requires two things. So a store requires the value to be stored. So the value to be stored, actually let's go back. Let's go back to this point where the register that contains the value to be stored is the RD field in the instruction, bits 23 to 26. So if the instruction is a store, then this value will flow to the register file, and the output will be OP2. So basically OP2 contains the value that needs to be stored. So this is the store value, and the memory address is there in the ALU result field. So the ALU result field that contains the address, so this ALU result contains the address for both loads as well as stores. So in this case, the address gets stored in the MAR register inside the memory unit. which is not visible outside. So it's just a staging area. And the data that needs to be stored is stored in the MDR register, which again is the staging area. So the address flows to the data memory, and the data that needs to be stored flows into the data memory. So inside the memory it's stored, and we get nothing as output, right? So basically the store instruction does not produce any output at all, and the job of the instruction at this stage is over. So the memory unit is very simple. In the case of a load, it takes an address, returns a value. In the case of a store, it takes a value as well as an address and performs the operation. There are two control signals that control the operation of the data memory: is load and is store. They are again generated by the control unit. Now let's take a look at the register write unit. It's also known as the writeback unit. So this is slightly more complicated. So let's take a look at the register file. So inside the register file, we have seen our inputs, but we are not. So we had essentially see the read inputs, but we'll also have to write into the register file. We are not taking a look at that, but we'll take a look at it now. So basically there were two read ports. A port is an interface. So there were two read ports, read port 1 and read port 2. So read port 1 took in an address, and it essentially gave out the data, right? So similarly read port 1 took in an address and gave out the data. So the register file also needs a write port where we will write in something. The value of the value that was computed needs to be written into the register file. So in this case, we need to we actually need three inputs. The first input is the enable input. So the enable input means that we want to write something. So enable was not required in the case of a read, because what is the worst that can happen in the case of a read? We'll read junk, which is fine. We'll not use the junk later. But in the case of a write, we cannot really afford to write junk, right? So that is not possible, it is not advisable, and it's also not correct. So we need a is WB, is writeback signal from the control unit, which will tell us whether we need to write into the register file or not. And there are some instructions where we write into the register file, such as add, subtract, multiply, divide. There are many instructions in which, however, we do not write to the register file. For example, a store that we saw in the last slide, or a branch instruction, we do not write into the register file. So that's the reason, the is writeback signal is important. Next, we need to consider the address. So address basically means which register we want to write to. It's not a memory address, it's a register address. And since simple RISC has 16 registers, a register address is 4 bits. So we have a choice here. So we can choose between several things. So one is that we take the default register destination, which is RD, the RD field in the instruction, bits 23 to 26. So that is the default. The call instruction is very special in the sense the call instruction, what it does is that we jump to a function, execute all the things in the function, and at the end we call a ret instruction, and the ret instruction we come back to the instruction just after the call. So what we essentially do is that when we call a function, we are supposed to write the address of the return address into the RA register or 15. So the call instruction is associated with the register write, because the return address, which is the next instruction after the call, its address needs to be written into register R15 or RA. So thus a register write is involved. Hence, we have the is call control signal generated by the control unit, which chooses between R15, the return address register, right? Which chooses between 15, which is the ID of the return address register, and the default register destination field, which is bits 23 to 26 inside the instruction. So we choose between them, and this becomes the ID, the address of the register, right? So it's a 4-bit quantity. So all of this, all addresses are 4-bit quantities, right? This is also 4 bits, this is also 4 bits. And all outputs are 32-bit quantities. Next, since we are writing, we need to write the result. What is the result that we want to write into? So we need to write in 32 bits. This is slightly complicated, not all that hard. So let's see. So we need a multiplexer, but what are we choosing from? So we are choosing first between the ALU result, which is the result that the ALU is producing, and this will be the case for add, subtract, multiply, divide, all arithmetic and logical instructions. The result will be the ALU result field. So that is one. The other is the load result, which is pretty much the value of a load instruction that you read from memory, right? In the previous stage, in the MA stage, the value read from memory. Or in the case of a call instruction, right? So consider a call instruction. If its program counter is PC, then we need to have PC plus 4 as the return address, and the return address is which is PC plus 4, which is computed at this point, is essentially the value that needs to be written to the register file for the call instruction, right? So you can call this as basically the return address, right? The return address for the call instruction. So we basically have 3 choices. What are the 3 choices again? The first choice is the results produced by the ALU, right? The ALU result. The second choice is the value read from memory in the case of a load, called load result. The third choice is the current program counter plus 4, which is the return address in the case of a call instruction. There are 3 choices, so we need 2 bits to choose between them. So let's use 2 control signals, isLoad and isCall. If both of them are 0, we choose the ALU result. If isLoad is true and isCall is 0, it means it's a load, so we choose a load result. If isCall is 0, means that it's a function call, and if isCall is 1, which means that it's a function call, and isLoad is 0, we choose the third input. And after choosing, the value is called result, and that is what is written into the register file. So this pretty much takes care of this discussion of ours that we have been having for the last 1 hour. Pretty much covers all the 5 stages of the pipeline in a fair amount of detail. So the detail is enough to actually implement this in actual hardware using a hardware description language. So what I would suggest is that readers can take a look at Logisim. So Logisim is freely available on the web with an open source license. So readers can take a look at Logisim because it's very easy to use, especially for first timers. So they can design this circuit on Logisim, and so basically this circuit will work as is shown. So essentially everything that is shown has just to be entered into Logisim, and Logisim has good support for drag and drop elements, so it is possible to design multiplexers and so on. That is one option, and for those who know hardware description languages such as Verilog and VHDL can also implement it. You will find a Logisim model of this processor and a Verilog VHDL model of this processor on the course website, and so that can be a good starting point. A VHDL model. Okay, so now it is time to summarize whatever we have done. So this is pretty much our design as up till now. So the top parts, I'll not go into the details, it's not required. We have discussed all of this. So this is the fetch unit. Then we have, so I've just taken all the individual diagrams and made one large diagram, that's all, and nothing more. So this part is the OF unit, right, along with the control part. which the control unit is thought of as a black box which generates, all of these signals to control all the multiplexers. So if you see, all the multiplexers are controlled by these dotted lines generated by the control unit. Then this part is the EX stage. And this part is the memory access stage, the MA stage. And finally this part over here, which sends all of its data back to the register file, is the RW stage. So we have discussed all of this, and but this is just showing you the entire process. Let me remove all my annotations and again go back to this beautiful design. So this is a processor for you, pretty much, and this is strong enough, potent enough, capable enough to run the entire simple RISC ISA. And so there's absolutely no problem, and you will find models of this implemented in Logisim and VHDL on the website. So readers are more than welcome to try it out. Let us now take a look at the design of the control unit. So the control unit is very simple. It's a piece of logic. The inputs to the control unit are the opcode, the 5-bit opcode. So it bits 28 to 32 in the instruction, and the I bit, the immediate bit, which is bit number 27. The outputs are all the control signals that we would require. So basically, given the 6-bit input, the opcode 5 bits and 1-bit immediate bit, it generates all the control signals. So let's basically look at the conditions of these control signals. So this list contains all the control signals that we have seen in the in the past few slides. We have seen is store. So the conditions when the instruction is a store. Similarly, is load when the instruction is load, is BQ, BGT, ret. Is immediate is set to 1 when the I bit in the instruction is set to 1. The difficult one is writeback. So is writeback is set for those instructions which write to a register. So first, the instructions that write to a register are arithmetic instructions: add, subtract, multiply, divide, and modulo. Then they are logical instructions: and, or, and not. We then have the move instruction, which moves an immediate or a register to another register. Out of the two memory instructions, load and store, only one of them writes to a register. That's the load instruction. Store does not write to a register. Then we have the 3 shift instructions that write to a register. And we have already discussed the case of the call instruction, which writes to a register. So this is, mind you, implicit, in the sense that when we call a function, the return address is written to the return address register. We have discussed the case of is uBranch is unconditional branch. So definitely the B instruction will be in that. So B is for branch. So that will be covered. And this condition is also true when we have the call and ret instructions. So call and ret instructions are also unconditional branches. So that's the reason this instruction is also this instruction also comes in that. And so as we had discussed in the slides that when so let me go back to the execute slide. I had promised that we'll go back to it. So when we are discussing the branch unit, we had talked about the is uBranch signal. So the is uBranch signal happens when we are guaranteed that we'll take the branch, and that's possible for the B instruction and the call and ret instructions, because it is guaranteed that the value of the program counter will change. All right. Then the is call instruction signal is set when the instruction is call. Let's now take a look at so those were the basic control unit signals for the entire data path. But then let's look at the ALU signals. So the signals sent to the ALU. So we are look at so the isAdd signal is when you want the ALU to do an addition. That holds true for the add instruction as well as the load and store instructions, because it's necessary to add the offset to the contents of the base register. Then we have the sub instruction: subtract, compare instruction, multiply, divide, modulo, the three shifts, or, and, not, and move. So for each, so whenever the instruction is any one of them, we generate an appropriate signal. So what I have written on this slide is, so let's consider the 5 opcode bits. Let's call them OP5 to OP1 and the immediate bit I. So I've just written down the conditions for finding for essentially essentially detecting these signals, or setting these signals. So this condition basically means that if the OP5 bit is 0 and the rest of the bits are 1, 0, 1, 1, 1, 1, we have the isStore instruction, the isStore signal is set to 1. So similarly, there are conditions for the rest of the signals. Since the writeback, the isWriteback signal was complicated, it has a slightly longer form. So it is possible, so whenever such a circuit is being designed, so typically the control unit takes time to design. But since these Boolean equations are given, it is very easy to design this control unit in hardware. So it can be very easily done on with Logisim or any other hardware description language. All that needs to be done is that this logic, these equations need to be written and implemented in hardware. Alright, so this brings us to the end of the chapter of processor design with a hardwired control unit. So we shall now look in the next part on microprogrammed processors, which are a different kind of processors that are far more flexible, and are a large part of it can be changed by the programmer, but their performance is somewhat on the lower side.